in the next subsection, we'll talk about the Lempel-Ziv-Welch algorithm, which will be a whole family of, it's a representative for a whole family of algorithms invented by Lempel and Ziv in the 70s, which forms the basis of many compression methods. In particular, the famous zip algorithms are based heavily on Lempel-Ziv style compression. As a warm-up, I'd like you to look at this poem which has been compressed. And it's very fitting. I used this example before I moved to the UK, but now I actually learned where this infamous peas porridge is actually made. Somewhere in the northeast, I learned. So that's apparently what it looks like, which is not very relevant for compressing, but still you might enjoy this this piece of trivia. So look at this picture, and well, to get you started, I'd like to have you answer this question. So the second to last line of the poem will be the one that we're interested in. And without much of an explanation how this works, I just want to start the Pingo question about this, and yeah, take your time. That reminds me, I didn't start the login. We'll do that after that question. Okay, I'm having trouble with Pingo again. So I'll just have to set this up. Okay, you should see the question now. For some reason it didn't show up in my list. Probably got the tags wrong. But so here's the question. You can just enter text, and I'll give you a little more time for this. I definitely forgot the Pingo attendance login. I'll do that after that question. All right, I don't know how the lag is today, how much of a delay I have. So maybe again, if you let me know if you're done with answering the question, that could be useful, so we don't spend all time eating peas porridge. Okay, some people done. I'll take this as a sign to go back and give you like 10 more seconds. 8, 7, 6, 5, 4, 3, 2, 1, and that's it. Okay. Again, this, okay, it doesn't, whatever the spelling is, a couple of people got this right, and okay. So let me, before I forget it again, start our login question. All right. So I guess you figured out intuitively how this compression method worked for this poem. You just have boxes around individual letters or entire, well, substrings. And you could use these arrows to copy an entire phrase. And so you get this whole poem compressed to, well, just representing a small subset of all the letters explicitly. It's not completely compressed. You could save a few more letters if you wanted, and that's a fun exercise if you want to do this. Now, why do we do this this gaming? In case I'm not sure if you can read this. In case you haven't heard of this, there's a nice website called Computer Science Unplugged, CS Unplugged, which is basically about teaching material for elementary schools and high schools, teaching computer science without computers. Which sounds a bit weird, but if you think about what we do here, computer science is a lot more than the technical aspects. It's got a lot to do with abstract and math and algorithms and so on. You can do a lot substantial computer science education without computers. So this makes a lot of sense, and they have many creative exercises, including this one about compression. So I'm presenting this this exercise to you because that's the essence of Lempel-Ziv compression. You copy a phrase that you've seen before in the input, and instead of writing it down again, you just copy the reference. Now, of course, we'll have to get a little more detailed, a little more precise about how to do this to make this an algorithm. But that's the essence. So if you keep anything in mind from this section, definitely the picture with the piece part should be the one. Okay. To set this in context, we've been talking about Huffman codes last week and about run length encoding yesterday in detail. What they do is they take advantage of single characters that are either more frequent or less frequent than others, or are repeated for the runs. But that's usually not enough. That's not good enough in the case of this poem, even though the poem was repetitive. There was not long runs of single characters or a very, very skewed distribution of the characters, of their frequency of occurrence. But instead there were substrings that occurred several times. And this is very common. English text has a lot of copies of these words that are very frequent. If you have a website in HTML, it will have lots of occurrences of these little substrings and many others in particular. So include XML, HTML if you like. Proper HTML should be a valid XML document, whereas XML is more generally used for transferring structured data via the web. So in a sense, also XML has the feature of HTML that many of these tags are copied. So in a sense, we have to look at substrings instead of single characters. And this is what Lempel-Ziv is about. Lempel-Ziv, as I said, is a whole family of algorithms. It's not a single method, but things that are united in spirit, if you want. The idea, as in the example with the poem, is to store repeated parts that you've seen before by a reference instead of writing them down again. Now, in this case, we will need code words for certain parts of the text. So whenever we store something, we write down a code word. And now code words can refer to a single character or a whole substring. That's exactly the meaning of this reference. We use a code word to encode a reference to a substring that we've seen before. And now this is something that we didn't have before, which makes this an adaptive compression algorithm. The dictionary that we use, or the mapping from things to code words that we use, will have to change over time, just because the part that we've seen from the text changes from each step to the next. This is something where we have to be careful that both the encoder and the decoder see the same sequence of changes. Otherwise, it's not possible to decode our nicely compressed text. There's a whole family behind Lempel-Ziv. There's the two more original variants. that are called Lempel-Ziv-77 and Lempel-Ziv-78, just essentially giving reference to the two papers where they mostly discussed these. And they are used as they're described in the original paper in some of the tools. Especially some of those are library implementations of zip, which again are used in some programming libraries. So these are useful by themselves. But the method I want to present to you here is the Lempel-Ziv-Welch variant. All are fairly similar. All have the same kind of all have the same idea of reproducing substrings that we've seen before and using a reference to them instead of writing them down again. But the details differ in each of them, and my meaning on this is that the Lempel-Ziv-Welch algorithm is the most elegant or most cleanest version of this. We could have discussed the others too, but I think this is the one that's best to explain. Okay, enough about the motivation for this. As you might have noticed, unlike the character encodings, the Lempel-Ziv-Welch method is a variable to fixed encoding. Variable means a variable size portion of the source text is encoded, and fixed means with a fixed length code word. Huffman was the opposite. It was a fixed to variable. Maybe something to note. I'm not sure if I had that on the slides, but it will appear at the end. Just to contrast the two. In Huffman encoding, we had a single character represented by one code word, but the code words could have different lengths. Now it's the opposite. We have variable length parts of the source text, but then we represent them with a fixed length code word. And you'll have to think about how to do this. A typical choice is that we use k bits, 12 bits for the code words. But that's a tuning parameter. Now, how does this work? Now, this is the point to wake up. I've been talking a lot about the history of this thing, but now we really get to the essence of this Lempel-Ziv-Welch method. We maintain a dictionary. That's a list of code words that we have so far constructed. And as I said before, the dictionary is adaptive, so this will change. But it will have space for 2 to the k entries. The code words themselves are simply indices in this dictionary, so we just number all the rows in the dictionary, and the code word is the index. The dictionary is not initially empty, but it contains all the characters in our alphabet. So when we get started, we have one code word for each of the characters. That seems reasonable because we have to get started somehow. Now in each step, we will encode a certain substring. Now I'm looking at the picture here. In the general case, each step will encode some part that we've already seen. So we will just encode a reference to an earlier code word, but we will also use the next character in the source text. And here the real difference between Lempel-Ziv-Welch and the other variants is how these are handled. The part that we copied identically is what we actually store as part of the coded text. So we encode in this example just the part ban, but we add a new phrase to our dictionary, which consists of the copied part plus the next character. And the idea behind this is we've currently seen ban, and we've seen the same ban before. Now, if we've seen ban now, it's likely that we will see also banna in the future again. So it makes sense to create a phrase, create a code word that represents banna in the hope that we will use it again. That's the idea. Now you might ask yourself, why not always also encode the A? The problem with that is we don't know what the A is. The copied part only extended till the N. So we would have to store the A too, and then things become less clear. So this is really the insight of LZW. What we encode is not the same as what we add to the dictionary. By keeping those two things separate, one step apart, we can avoid some of the tricks that other Lempel-Ziv-Welch methods needed. All right, so that means after each phrase that we encoded, we also add a new code word to the dictionary. If you really store this in computer memory, you would have for each code word, you would have to store the string it expands to. But here you can compress your own compression method. You don't have to store the string itself. You can store the reference x, which has to be another code word in the dictionary, and the next new character, just the C. All right. I guess this is best understood on an example. So let's work through that. We have an input string here, which is fairly repetitive, so that the interesting things happen early on. Here's the picture from before, and here's our dictionary. So initially we have, well, these are just empty spaces, but we have the dictionary pre-filled with all the characters in the alphabet. And in this case, I just assume it's all the ASCII characters, even though just a small subset of them occur here. But just to keep the example a little more realistic, we would usually have a large alphabet here pre-filled. Now, how does the encoding work? We find the longest such phrase, we find the longest thing we can copy from what we've encoded before, and the next character. At the beginning, there's nothing we can copy because we haven't encoded anything, so there's really only the C. So this is the C. What we do is encode the, in the special case that X is really empty, we encode the C because that's also a special case in the dictionary. So the picture is for the case where we really could copy something. If it's a single character, what we store in the coded text is exactly the code for this character, which is the 89 for Y. But there's another thing we have to do. We copied nothing, but well, the X in that case is, okay, sorry, that was not correct. This is X. Sorry, let me repeat this part. X is either the longest part that we could copy, or it is a single character. And in a sense, we copied something from the dictionary, and initially we have the characters here. So it does fit the picture. This is the general situation. We always can copy some non-empty string from the dictionary because we start with the individual characters. So X is Y, and we encode X, but the second thing we have to do is add XC to the dictionary. C is the next character in the string, so this would be YO. And that's what we do next. We add this string to the dictionary, so there's a new code word, 128, that we now assigned the string yo. All right? Let's do this one more time. We read the next character. Now, we couldn't copy something bigger than just a single character from the dictionary. Whenever you can start with the next phrase, you really look through your dictionary and find the longest string that's stored in your dictionary that starts at this part of the text that you haven't coded yet. And in that case, that's again just O, the single character. So this is our X. X is just O. So we encode x, O, which has the code 79. But again, we also have to change the dictionary. We add xc, and c, the next character, is the exclamation mark. So that's what we put into the dictionary. One more time. We start by finding the longest string that starts at this position in the dictionary. Well, the only thing we've seen is the exclamation mark itself. So x again is just exclamation mark. C is the next character, is the space. So we encode x, which has code 33, and we add to the dictionary the new code word exclamation mark space. All right. Next example, same game. The space didn't occur before, so we can only have a single character in x, but we add space y to the dictionary. So now things become more interesting. We start at this position and look for the longest string that starts there. That's in the dictionary. And here we actually find a longer one, not just a single character. So x is yo. And therefore c, the next character, is u. So we encode x, which has this code, 128, but we add xc, u, in the dictionary as a new code word. All right, I hope you see how this goes. The next example is again one u. We haven't seen u before, so it's a single character, but we add u exclamation mark to the dictionary. Next step is the exclamation mark and the space, which we've seen before. So we encode this, but we also add exclamation mark space y to the dictionary. One more time. Now we start at this position, and we've actually added u before. So now we can encode 3 characters with one code word. And we take the next character r and put that into the dictionary. That's how this goes. Next one, r will be the first occurrence of this character, has to be a singleton, but then we add r space to the dictionary. Now let's see, maybe we can make this a little more interactive. What would happen with the next character? I start here. What would be the next x? What would be the next code word that I can find starting at this position? Maybe you could tell me that in the chat and just ignore that German guy or lady who spammed our chat a bit. So maybe you can just type in the code of x, the next code. All right, 131. That sounds good. Sorry, this is not super interactive. Essentially, the first 2 guys who responded already dominate this. Maybe there's more people coming. Exactly right. The next thing we can find in the dictionary is space y, which has the code 131. And what would we add to the dictionary? The phrase we just had plus the next character. There you go. Okay. I guess by now this is fairly clear how it goes. O, we've had O before, but it was followed by an exclamation mark, so that's still the longest we can do. And then we're almost done. So once we're done with this, we have encoded this text with this code word. It's a sequence of integers, and these integers represent indices in the dictionary. That is the output of LZW encoding. If you spell this procedure out in pseudocode, it would look like something like this. I used the same variables that we've had in the example. So x is the phrase that we previously encoded, or the current phrase, depending on how you want to see it. C is the output, the coded text, and we have this dictionary. If you think about the operations, what we had to do here, at each step we had a certain position in the string, and we were trying to find what is the longest string in our dictionary that starts at that position in the text. That's essentially a string matching question, right? We were asking for a substring, except that it was a very, very simple version of the problem. We already knew the starting position. And then we had a whole collection of strings that might be the longest, but we want to find the unique longest one. And a smart way to do this is using a try. Then you would keep the dictionary, you would keep all those strings in a try, and you would traverse with the next, so say we're currently at this position, so you would follow the edge y from the root. That gives you all the strings that start with a y. Then you would follow the edge with an o. I mean, there's many more edges here going on with the other characters, going out with the other characters. YO, then there would be, for example, the 128 would be one leaf here. But there's also the U, so well, we might have dollar here, even though it's not drawn. So 132, that's not yet it. Okay, we need another internal node for U. So here you would have the 1, 2, 3, the dollar, and then there's still the your. So you would go with an R here. I guess you get the idea. So by keeping the strings of the dictionary in a try, we can efficiently walk down as we read the text, and we will automatically go to the deepest leaf as long as we can continue. So if we're stuck, we read a dollar and go to the phrase that stopped here. But if we can continue, we do so. So that will find automatically the longest match. That's why storing the dictionary in a try is a smart decision here. We also need a variable k for the next free code word, the next free number in our dictionary. And then we go through each position in the text. We look at the next character, that's the C. And now we check if, well, initially x will be empty, so if we're at the beginning, then we just take a single character. X is empty, C will be a single character. As long as we can follow an edge, so this is nothing but saying we can follow an edge in the try. So if there is an edge in the try with the right label, we follow it, and we will continue to do that with more characters. But at some point we will reach a stage where we cannot continue in the try, and at that point we will go to a leaf. So we will find for the previous, the x will always be the longest thing that we can find in the try, but xc then was not contained. Then we encode x, as I've shown you in the example, but we also add a new word to the dictionary, which is x followed by c. And then we update things for getting the next round going. So again, this code is the very same thing that I showed you in the example, but spelled out in a more structured way.